Alright, so now we're going to look at the Crank-Nicolson method for solving this problem in general, solving for the heat diffusivity over time, right? And so the way we're going to do this is we're actually going to rewind a little bit past where we kind of solved our previous one in the second video and where we ran into the issues with our R value, right? So the Crank-Nicolson method is actually going to be a way to reformat our equation so that it accounts for that failure of the R value, and our R value can now be pretty much any value. Basically, this equation works better. So we're going to rewind back to where we have our t n plus 1 j equals t jn plus our R value, which, if you remember, been sitting for too long. If you remember our R value, it is our alpha times the change in time over the change in x squared. And now, what we're going to do differently is, and I'm going to put this in parentheses basically, this is just going to, R value is multiplied by, and what we're going to do here is account for both our n plus 1s and just our n's using the same method. So let's start with our n plus 1s. So t j plus 1 n plus 1, and then minus 2 t j n plus 1 plus t j minus 1 n plus 1, and then this is plus, and now this is just our our current n value, so j plus 1 n minus 2 t j n, and sorry, I'm not doing too well on room here, but plus t j minus 1 n. And so this top part is all going to be divided by 2, because notice we have essentially, if you ignore the plus 1s on the n, we essentially have double what we had last time. But this accounts for essentially that next time, that one time stamp or one time frame in advance, right? So again, n is our number of timestamps, essentially, so this is essentially the next second, right? Our heat at that next time interval. So now, to make this look a little bit nicer, we can distribute our R value, and in order to distribute our R value, we just want it amongst the t. We can move this 2 up here, and so this essentially is going to equal our R value. And you can already kind of tell, compared to our other R value, which couldn't be greater than 1/2. This already you can tell it kind of accounts for that by having a 2 in the denominator. But let's look at how that affects our equation, right? So we are going to replace this with R, and then essentially we're going to distribute our R across all these t values, and then we're going to put all our n plus 1s on the right side of our equation where we have this, and all our t n's on the right side. So we have so negative r, right, because we're distributing it over. Negative r, t, j plus 1, n plus 1. And then plus 1 plus 2r. And then this accounts for both the tn plus 1 we've had here and the 2tn plus 1 we have right here. So 1 plus 2r, t, j, n plus 1. And Amara already telling me to run out of room, so I'm just going to make the most of it and then just do the other side of the equation down here. So we have net minus r, t, and then of course j minus 1, n plus 1. And that equals, down here, the other side of the equation, right? So we have r, t, j plus 1, n, and then plus 1 minus 2r, t, j, n, and then, sorry. Minus, or sorry, no, plus r, t, j minus 1, n. And then this essentially is, now since we have all our n plus 1s on one side and all our n's on the other side, this is actually a really good way to then kind of follow the same step as we did before, right? So remember when we took out a TJN, and then we were able to use Euler's formula to then substitute in with trig, with cosine, and then we were able to show that r had to be less than 1/2, and now we're going to do the same method to show that in fact r can be any value essentially. So let me real quick, I'm going to take out a t, j, n plus 1, and then our remaining plus 1s on the j, remember we can then substitute for our e to the I k delta x, okay? So, and then the minus 1 is going to be e I k, or negative I k delta x. And then that way we're able to substitute everything out. So let me take this a step down. T, j, n plus 1. This is the first side of our equation, right? And I'm going to try to simplify this as much to fit everything on one line. We go r, e, I, k delta x. Plus 1 plus 2r minus r e negative I k delta x. And I ran out of room again, so let's show the other side of the equation, which is t, j, n, right? And then we have pretty much the same thing except for our middle term. So we have r, e, I, k delta x plus 1 minus 2r and then, sorry, it's also plus here. And then r, e negative I, k delta x. Okay. So now we're basically, sorry, we're gonna use our cosine to we're going to input our cosine into this equation for our values here, and then that way we're able to look at how our R value can then be greater than 1/2, essentially, or we've solved that problem in that at that point. So I'm gonna create a little bit of space here. And then let me kind of rearrange the equation, right? So we had the one side with the t j m plus 1, which is again essentially what we're solving for. So we now have that. We're going to put that on one side, and then our other side, right, is equal to t j n, and now we have our cosine version, essentially, of our previous problem. So we have 2r cosine, and of course we have ik delta x, and plus 1 minus 2r, that carries down. Sorry, this is a little bit messy, I apologize. But that's over 2r cosine ik delta x, and then plus 1 plus 2r. And so essentially right now we've already we can already tell that our R value is now it can be any number. We don't have to worry about our value being less than or greater than this is supposed to be negative. I forgot to carry a negative down from here. Sorry. So basically the top section consists of all negative values. It will always be negative no matter the value of R, and our bottom section will always be positive. And that at the end of the day means that our value will always be negative, therefore less than 1/2, and we never have to kind of worry about our value being too high anymore. And so yeah, and now basically what we're able to do is create a matrix, and we'll do this in the next video in Python, but we're going to create a matrix to then look at T1n or T1n plus 1, and then we'll be able to solve for or not solve for, but we're going to be able to look at our heat diffusivity throughout our rod.